Today, we're taking a journey through the vast and amazing animal kingdom. We're going to explore how life went from the absolute simplest creatures you can imagine to the incredible diversity we see all around us. So let's just dive right in with a question. What in the world does a tiny sponge have in common with a giant whale? I know, it sounds kind of weird, but the answer tells us something really profound about life itself. And to find it, we've got to look at how scientists classify animals. You see, this isn't just about making neat little lists, it's about uncovering the epic story of evolution. And that kind of begs the question, right? Why even bother classifying animals in the first place? Well, it's because this system is like a giant family tree for all of life. It reveals the deep, ancient relationships that connect every single creature. At its heart, this system is a roadmap of life's history. It lets us trace the path from the earliest, most basic life forms all the way up to the complex animals we know today. It's a fantastic story of trial, error, innovation, and adaptation. Okay, so before we really start our journey through this roadmap, let's quickly look at the tools scientists actually use to draw it. There are a few key things they look for when they're trying to figure out where an animal fits into the grand scheme of things. First up is body organization, and this is all about complexity. Are we looking at an animal that's just a loose collection of cells doing their own thing, or have those cells started teaming up to form tissues, which then build organs, which then work together in these complex organ systems? It's a huge difference. Next, they look at symmetry. This is all about the animal's fundamental body plan. Can you divide it into two identical halves? If you can't, it's what we call asymmetrical. But if you can, the next question is, how? And this shows the two main types perfectly. Radial symmetry is like a pizza. You can slice it through the middle a bunch of different ways and get equal halves. But bilateral symmetry, that gives you a clear mirror image, a left and a right side. And this was a massive step forward because it led to developing a head, putting all the sensors up front, and allowing animals to move with purpose. And finally, a super important feature, the column. It sounds technical, but just think of it as an internal, fluid-filled body cavity. This was a genius innovation because it created a space for complex organs to develop and stay protected, and it marks a huge branching point on that evolutionary tree. Okay, with our toolkit ready, let's dive into the journey. We're starting right at the base of the animal tree with the simplest designs out there. Our first stop, phylum Porifera, otherwise known as the sponges. These guys are the real pioneers. They're still at that cellular level of organization, which means their cells haven't really formed specialized teams yet. They're asymmetrical, no true organs, and they are absolute masters of filter feeding, basically acting like living water pumps. All right, the next big evolutionary leap brings us to phylum Cnidaria. We're talking jellyfish, corals, and sea anemones. Now, for the first time, we see true tissues and that radial symmetry we talked about. But their real innovation, their secret weapon, microscopic, venomous harpoons they use for hunting. How cool is that? Okay, let's keep moving, because the next set of innovations, a brand new third cell layer and a whole new body plan, completely changed the game for the entire animal kingdom. Say hello to phylum Platyhelminthes, the flatworms. These guys bring 3 total game changers to the table. 1, we now have organs. 2, they've got that bilateral symmetry, giving them a clear front and back. And 3, they have a third layer of cells, the mesoderm, which is the crucial middle layer that lets you build things like muscle and complex organs. Oh, and being flat, that's just a clever way to get oxygen without needing lungs. Next up, phylum Nemathelminthes, the roundworms, and they introduce 2 huge upgrades. First, they have a sort of prototype body cavity, a pseudocoelom, which gives them some internal space. And second, a complete, one-way digestive system. Food goes in one end, waste comes out the other. This tube-within-a-tube design is so efficient and successful, you can find these worms literally everywhere on Earth. So once that true body cavity, the coelom, was established, evolution could really start to experiment. It's like the floodgates opened, leading to an explosion of even more complex and wildly successful body designs. And here we go, phylum Annelida, the segmented worms, like your friendly neighborhood earthworm. Their big idea was segmentation. I want you to think of it like building a body from a series of repeating, modular Lego bricks. This allows for way more precise movement and makes them incredibly tough. Plus, they developed a closed circulatory system.
basically an internal highway system for moving oxygen and nutrients around efficiently.
Now, the next group we're going to look at, well, they're not just successful. They are, without a doubt, the single most dominant group in the entire animal kingdom. They are so incredibly numerous that they make up over 80% of all known animal species on our planet. Any guesses? We're talking about phylum Arthropoda, the insects, the spiders, the crustaceans. Their unbelievable success really boils down to two brilliant innovations: a tough, protective external suit of armor called an exoskeleton, and these incredibly versatile, jointed legs that can be adapted for walking, swimming, jumping, you name it. They are the true conquerors of the planet. Next up, we've got phylum Mollusca, the soft-bodied animals. And this group is all about diversity. They share a basic body plan: a muscular foot for moving, a central part holding the organs, and a mantle that often makes a protective shell. But that simple plan has given us everything from a slow-moving snail to the ridiculously intelligent and shell-less octopus. All right, let's move on to phylum Echinodermata. Now, these guys, they are basically nature's hydraulic engineers. Starfish, sea urchins, they all have this spiny skin and a totally unique feature: a water vascular system. They literally pump seawater through a network of internal canals to power thousands of tiny tube feet, letting them move and hunt. It's pure hydraulic power. This incredible journey has all been leading somewhere, and it now brings us to the final, and for us, the most familiar phylum of them all. This is our group. Welcome to phylum Chordata. Every single animal in this group, and yep, that includes us, shares these four key features at some point in their life. There's a flexible support rod called a notochord, a hollow nerve cord running along our back, slits in our throat, and a tail that goes past the anus. This is our fundamental blueprint. Now, within the chordates, one very special group evolved: the vertebrates. They got a major upgrade, replacing that flexible notochord with a bony backbone. This allowed for much larger bodies and way more mobility. And that innovation sparked another huge evolutionary wave, leading to all the classes we know today, from fish to amphibians to reptiles, and finally to birds and mammals, like us. So, when you step back and look at it all, what's the big takeaway? This journey from a simple sponge to a complex mammal, it's not just a list of scientific names. It's a story. It's our shared history. And it shows us, without a shadow of a doubt, just how deeply and beautifully we are connected to every other animal on this planet.